We are the rocket design team.
And we are the multi-rotor design team.
And this year, we will be collaborating as the Advanced Aerial Vehicle Group 2.0 to participate in the Argonia Cup competition.
Over the last year, we've been working really hard to improve our designs. Here are some of the things that we've been improving on.
For this year's competition, we have started electronics earlier in the year to prevent rushing them right before competition. We plan to practice integration and will ejection test prior to arriving on site. We will use flame shields to protect our parachutes from burns during ejection. Already, these changes have better prepared us for this year's competition and will aid us in our success in the coming weeks.
All right, so the multi-rotors team's primary improvement for this year is here in the release mechanism. Last year it was a fairly complex system and ultimately led to the failure of that attempt. So what we tried to focus on was simplifying it as much as possible. Basically how it works is there's a servo that has a cam on it where the string can lock in place and the servo spins. It's then held in and the drone is supported from a string that is mounted to a fixed point in the rocket. When the rocket separates, the servo can be unspun, the string is released, and the drone can drop out.
This is a concept of operations for the flight of Gemini. It shows each crucial event of flight. It all begins at launch. Once the motor is ignited, it will burn for 2.27 seconds. The rocket will continue to travel upward after motor burnout for approximately 20 seconds. Then, the rocket reaches apogee, which is the maximum height of the flight.
The drogue chutes will eject at apogee. The airframe will split into two separate pieces, and each piece will fall under drogue parachutes. Sometime between apogee and 1,500 feet, the release mechanism will allow the quadcopter to leave the rocket and fly away from the airframe components. The main parachute will eject at 1,500 feet. The quadcopter will fly to the target and the two rocket pieces will land safely and be recovered.
This is Gemini. She is 110 inches tall with a 5.15 inch outer diameter. The total weight with the motor is 32.3 pounds. The airframe is primarily fiberglass, strengthened by carbon fiber and epoxy resin. We are using an Aerotech L2200G motor with a total impulse of 5,104 Newton-seconds and a 2.27 second burn time. There are 3 birch wood fins with a carbon fiber layup to increase strength and keep mass low. The lower section of the rocket holds 2 parabolic parachutes, a drogue that deploys at apogee and a main that deploys at 1,500 feet from the ground. They are ejected using black powder charges. We have 2 electronic bays, one for each set of parachutes. This bay uses an RRC3 and a stratologger for avionics.
This 14-inch section of the rocket holds the quadcopter. In order to protect the quadcopter, the airframe is separated by CO2 charges instead of black powder. This is the second electronics bay. We are using another RRC3 and a Raven 4 for avionics for the upper section of the rocket. Here is where the second set of parachutes lie. They are almost identical to the other parachutes, but slightly smaller because they will only carry the upper, lighter half of the rocket. These parachutes will be deployed via black powder ejection. Finally, our nose cone is a 27-inch Von Karman nose cone with an aluminum tip.
The flight simulation from OpenRocket predicts 21.4 seconds to reach an 8,769-foot apogee with a maximum velocity of 1,053 feet per second and a maximum acceleration of 21.5 Gs.
Our team's responsibility is to maneuver the golf ball back to the landing zone after a rocket has done their part and put us up in the sky. This is Cuddlefish, our solution to do this task. It is a custom-made folding quadcopter that folds up small enough to fit inside of a rocket tube while unfolding with enough power to get us where we need to go. On board, there's a suite of sensors and systems designed specifically with this task in mind. We have a long-range radio communication system that can communicate with the aircraft up to 15 miles away. We also have a digital video transmission system that will give us a video feed from the entire time we are in the sky. As well, we have a GPS and RTK system that will make sure that we always know where we are.
We're excited for our second opportunity to participate in the Argonia Cup competition. This year, we hope that our results can reflect on our improvements. Let's go! We got this. We got it. We got it.